Okay, so we're going to add some tools to our discussion of probability. And what we're going to look at is conditional probability. So we're going to come up with a new notation here. We're going to say the probability of event B given that event A has happened. For an example, let's think of a deck of playing cards. Now, a deck of playing cards, there are 52 cards, and each card is different. It has some divisions. There's 4 suits of hearts, diamonds, clubs, and spades. Let's see if I can get my spade drawn right. And sorry that these are bigger; they were harder for me to draw. And these are kind of based off of a lot of randomized games like dice games and card games have religious and parallels through different cultures, where the things that we use were used to also make predictions or what do we call it when divination. In fact, a lot of the notation for some computer theory and logic comes from African divination and geomancy, earth, quote-unquote magic, which were actually random number processes that were done in religious ritual. Making things random and seeing and then in reading the results is common to many world religions. And this is one of the places math shows up a lot. In the past, we didn't have separate schools of thought between religion and mathematics and science. And so you studied religion and you were a priest, you knew the mathematics, you used them. They were all part of the universe, which was part of your theology. And so playing cards and tarot cards all kind of have a common origin. And randomness is actually kind of in that origin. But so this was for health, wealth. If someone's hitting you with a club, you're being oppressed. And if you're using a spade, which is like a shovel, you're doing a lot of work. So, adversity and hardship. Okay, kind of how those will cross. And then within each of those suits, so 4 times, there are 13 faces on the cards. And that's an ace, a king, a queen, and a jack. And then 10, 9, 8, 7, 6, 5, 4, 3, and 2. The ace can be a 1, or it can be the highest card, depending on the game you're playing. But these 52 cards, ace of hearts, ace of diamonds, ace of clubs, ace of spades, and so on, make up a deck of cards. So if I were to shuffle a deck of cards, and my chance of picking up a king of hearts is 1 in 52. That's my probability. But if I picked up a king of hearts, the chance of me picking up a queen of hearts in my next draw, if I haven't put this card back in the deck, so the probability of drawing a queen of hearts, given that I've already drawn the king of hearts, is equal to 1 in 51. Because taking this out of the deck changes the sample space. I have 1 less card in the sample space. And so this queen of hearts is still there, but my chance of getting it has been is slightly better because there's 1 less card. And so this is what we mean by conditional probability. Notice this notation doesn't do anything for us. There's no method to go out. There's no computation to make yet. We'll get to the computations for it. It's a way of telling us that this has happened after this has happened. And it's up to us when we are figuring out what the sample spaces are and what the outcomes are to keep track of it. Right? And so this is, without replacement, we say. If I grab the first card and I don't replace it in the deck, this is my chances. If I did replace the card in the deck, my chance of drawing a queen would be 1 in 52 because I now have 52 cards in the deck. And so this notation helps us keep track of that. I'm going to go over to a graph here because there's something nice that we can do with this idea of conditional probability if we have data. And so what we're going to do is we're going to look at, let's get it up here. I think I had that on this one. Yep. Here is some data. This is data that came out. People were surveyed if they were offended by something on social media. And in the survey, it was kept track of if they were male or female. Now, we can go into this data and we can do something really neat. We can say, all right, I'm going to pick only the responses that were yes. And let me see if I can get my pen to work here. There we go. I'm going to pick only the people that said yes, and I'm going to see how many of them were male. Right? Let's see that. And so I'm making a conditional probability. I'm saying, what is the chance that given that they were offended by social media, that the person was male? Or I would say this in my probability language. What's the probability that they were male given that they were offended? They said yes on the chart. And so let's come back over here and look at this chart. So given that they were offended, I'm looking down this column. And this says that the number of men or males that were offended was 532, and the total that were offended was 1,151. And so this becomes, thought I had that show up here. I didn't, so I'll say that again, making sure I click on the right things. I noticed this. So we're looking at this column of data, and so we're saying, given that you were offended, how many were male? And that's 532 out of the total number that were given that were offended. So switch back. And that's 532 out of, was it 1151. But let's compare this. Let's see the opposite. Let's say how many were offended if they were male. And so given that they were male, how many were offended? Well, look at how this changes as we look at our data. There we go. So now I'm saying I'm given that they were male. Well, notice my sample space is smaller. The men are 1,108 versus the column we looked at before. And if they're offended, well, it's still that 532, but out of a smaller sample space. And so this is 532 out of 108. Notice we're asking a different question of our data. Same data, but we're asking a different question. And it gives us a different probability. And this is a really important part about this notation, especially in descriptive statistics and what we can infer from this. This is saying, if we look at the people that are offended only, right, this percentage holds for the men. But if we look at men, this percentage holds for their chance of being offended. And so let me turn this into percentages so we can get a mental feel of this. I'm going to approximate these numbers. Grab my calculator here. There's the calculator. Sorry. There we go. Why am I not? See if I can get that to work now. There we go. So 532 divided by 1151 is approximately 0.46. There's more numbers out of here, or we'll say 46%. And 532 divided by 1108 and 0.48, or approximately 48%. So it's closer to being a true 50% of men are offended, even though the number of people offended are less. Right? So notice the phrasing here. If I grab men, that's the percentage who will be offended. If I grab offended people, that's the percentage that will be men. So this notation lets us ask and display the results of asking different questions. And I think it's a really important distinction, and using these graphs is an important way of doing it. I'm going to pull the graph up again, and notice that our questions kind of come in columns. Given I'm in this column, right? Or columns or rows. Given I'm in this column, what are my chances of being these things? Given that I'm in this row, what are my chances of being these things? And so columnizing our data is a good way of kind of looking for these relationships that can come out in conditional probabilities. All right. So I already showed it with cards, but we're going to talk a little definition here, and that is independent events versus dependent events. And so events are independent if the outcome of one does not affect the other. Right? The outcomes do not affect the results of one or the other. So the occurrence of one of the events does not affect the probability of the occurrence of the other event. And we write that mathematically as the probability of event B given event A is just the probability of event B. A doesn't matter. Or the probability of event A given event B is just the probability of event A. And so that's how we would notate independence of events. Events that are not independent are called dependent. And so events where the probability of B given A does not equal the probability of B, or the probability of A given B does not equal the probability of A, these are dependent events. And that's something we have to determine when we look at events. We'll get some practices with that as we work on different problem sets. And so I did that with the selecting the cards from the deck. If I put the card back into the deck, it becomes independent. So let's just give that idea again. If I have a deck of 52 cards, right, they're all unique, and I shuffle them up so they're random, the probability of drawing a Queen of Hearts, given that I've drawn a King of Hearts without replacing, is 1 in 51 because it's dependent. And in particular, this dependency changes the sample space. Right? I start with 52 cards, I dish one out, and now I have 51 cards. And so that changes the sample space. I still only have one Queen of Hearts in there. Now, some of our dependencies might change both the number of outcomes in the event and the sample space. And so it's up to us to kind of keep track of what the given probabilities can be. Another example is, I'll go back to, I flip a coin and roll a die. All right, we did that in the previous lecture. So what's the probability that I roll a 3 on a d6 given that I flipped heads? Well, if I flip tails, the die's still going to only have one option there out of 6 outcomes. That probability is still 1 in 6. In fact, that is equal to the probability of rolling a 3 on a d6. And so this is independent. And so our probabilities can influence each other, but they don't have to. All right, and we use the word dependent and independent to determine how probabilities affect each other. So, if probabilities will happen in sequence, will be what we look at in the next lecture.